Hello and welcome to a new lecture about probability and statistic coding in Python. In the previous lectures, we practiced basics of statistics, visualization for descriptive statistics, set operations, counting, permutation, and combinations, and also conditional probability. And today, we are going to practice discrete random variables. In the theory lecture, we learned that a random variable is a numerical outcome of a random process. And in the case of discrete random variables, we are going for countable. For example, rolling a die produces a random variable and it can take values like 1, 2, 3, 4, 5, and 6. Today, we want to do coding in Python. We will start with a simple example to represent a discrete random variable in Python. To do that, we import random. So this random imports the random module to generate random numbers. Then we define the possible outcomes of a fair die. So outcomes, we can say O equals to 1, 2, 3, 4, 5, and 6. These define the discrete set of possible values for the random variable that we have. Then we go for simulation of rolling the die 10 times. So we can say R is equal to random.choice, and here from outcome 4 underscore in range of 10. So what we did here, these are R that we defined here. These generate 10 times out of this one. Randomly, we select from this one, right? We used a least comprehension to simulate 10 rules by randomly picking from the outcomes that we have here, right? Then we can print these rules. For example, we can say print and we can say, for example, the rules of a fair die, and in here we can go for R. So first time it's a kind of simulation, right? First time it was 5 randomly, 3, 6, 4, 2, 6, 3, 2, 1, 6, right? It's a fair die. It means the outcome is equally likely. Then we can go for flipping a coin as well, right? So in this case, we can say coin outcome is what? Is heads or tails. So we can say only 0 and 1, right? Then for flips, we can say like flips, then the same. We can say random.choice. This time we go for C underline O and 4 in range of 10, right? So we simulate. This time we can go for 5. We simulate 5 flips using least comprehension, right? Then we want to sum the least to count heads, like for example 1, right? So we can say heads is equal to sum of f, right? And here we can print h. So it was 3 times we had heads, right? Because 1 is head, right? If you want to print them, you can say like f. So it was head, head, tails, tails, heads. So 3 times it was heads and 2 times it was tails. Then we had the concept of probability distribution for discrete random variables. We learned that the probability distribution assigns probability to each value of a discrete random variable. For example, for the same case that we had outcomes of 6 here, or of 6, we will bring it here. And suppose this is an unfair die. It means we have some probability. And in here we say probability of having 1 is 10%. Probability of having 2 is also 10%, but the rest is 20%. So it's unfair die. For 1 is 10%, 2 is 10%, 3 is 20%, 4 20%, 5 20%, and 6 20%, right? So in here, we can go for rules and we say, again, random.choice from outcomes, and we give some weights. So weight is the probability that we defined as unfair. And in here, we also say k is equal to 1, 0, and 4 underscore in range of like 10,000 times, right? So I explain what happened here. So this one's to the choices. So here, what we did, we simulate 10,000 times with given probability that we have defined here, and we extract the single choice for 0, right? This is a single choice. So here we have k equals to 1. It means one element is chosen at a time, and this 0 is used to extract the first and only element from this list. This gives us a single outcome as opposed to a list of outcomes. For underscore in range of 10,000, this is a list comprehension that repeats the process 10,000 times, generating a total of 10,000 outcomes, right? So then I want to calculate the frequency here. Frequency is compute the simulated probability for each outcome by counting the occurrence of that outcome. So f is equal to r dot count x divided by, for each one, divided by 10,000 times the total that we had for x in O, right? This way we calculated frequency. Then we go for plotting. So for this one, we need to import matplotlib.pyplot as plt. Then we say plt, we want to have a bar plot. Bar plot of outcome, probabilities, and alpha is equal to 0.5 as the transparency, and we label it as, for example, theoretical, right? Theoretical, it means what is expected to be, right? It's not what really came from the simulation. So we can say theoretical. Also, we make a bar plot of simulated. It means we want to overlay simulated probabilities which really came from out of the simulation. So we say O and F, alpha is, for example, 0.5 label, this time simulated, right? And we don't need this one here. We say outcome probability, and this one we can plot it. So I will explain what happens here. Theoretically, it is based on these probabilities. But because we are going to use random, so the outcome is maybe a little bit different by theory, right? So we use a frequency here to go for the probabilities. And you can see here simulated is this color. You can see a little bit is different here because randomly we selected a little bit different here, different here. So you can see the probability of 1, probability of 2 is theoretically a little bit more than what we got in random. So this is how we can plot the probability distribution for discrete random variable. Then we want to go for CDF, cumulative distribution function. We learned already in the theory lecture that CDF gives the probability that a random variable is less than or equal to a value, right? And we had an example like a store carries flash drive with either 1 gigabyte, 2 gigabyte, 4 gigabyte, 8 gigabyte, or 16 gigabyte of memory. We had a table, and in the table we had something like this. So y as 1, 2, 4, 8, and 16. And the probabilities of y was something like this. It was 0.05, then 0.1, 0.35, 0.4, and 0.1. So this was our table. And then we had cumulative distribution function. We have calculated cumulative distribution function. and it was something like this, that in LaTeX form, in the markdown, I say if y is equal to begin cases 0 and y less than 1, then new line, then 0.05, 0.05 and 1 less than or equal to y less than 2, then in 0.15 and 2, then less than or equal to y less than 4, then new line, then 0.5, 0.5 and 4 less than or equal to y less than 8, then 0.9, 0.9, and there must be an end here, and 8 less than or equal to y less than 16, and 1 and greater than or equal to y less than 16, right? Then in here I say end cases. This is LaTeX coding and we use in Markdown. So what is the output here? 0, 0 for y less than 1, then 0.05 y between 1 and 2, 1 is included, then 15, 2 less than or equal to y less than 4, then we have 0.5 y between 4 and 8, then we have 0.9 y between 8 and 16, and 1 for this one is wrong. This one should not be here. So this is what we have. No, y we have should have here. Should have a y here. Okay, this is our CDF, and now we want to plot it. We define a function and we call it as, for example, plot CDF. Okay, then we define y values and corresponding CDF. So y values are what? 1, 2, 4, 8, and 16. And CDF values are what? We have them already here. Okay, now we can extend the range to include the starting and ending points as well. So we can say y values is equal to, for example, 0 plus y values plus 20, right? Then also we can do the same for the CDF values 0 and plus 1. Then we want to plot. So we want to plot the step function. So for I in range of length of our y values minus 1, then we will plot plt dot horizontal lines CDF values I and y values I, and then y values I plus 1, and we can say line style, for example, we can say dashed line styles, and color also is equal to, for example, blue, right? Then, as you know, we have some markers for the step changes as well. So we go for a scatter plot, right? So we go for a scatter plot and we say y values and minus 1, and also CDF values the same, the other side, and color is equal to, for example, red, and z order is equal to 3, right? Then we can add also some labels. PLTX label is Y, and PLT Y label as FY, title, cumulative, distribution function, grid also we can have. Then we can call our function plot dot underscore CDF for CDF. So here we go. We made a mistake. It should not be like this. So where is our mistake? I need to find it. So I made a mistake here. This one should be 15. Then here should be 0.5, 9, and 0. Right? Again, some problems are there. So the CDF should be exactly like this. 4, 5, 15, 5, 9, and 1. Okay, it's all. Right? So we have mistake in these probabilities. So you can see here it's like a step function. So you can see up to here 0, right? Then we have here, so from between 1 included up to 2, right? So 1 included up to 2 is something here, let's change the sticks. So for example, here I can say plt.xsticks. Let's import NumPy first here. Import NumPy as np. Then in here we can say np dot a range 0 to 20, and each one by a step size of 2. So you can see here what happened. For less than 1, it's 0. So you can see for less than 1, it's 0 if 1 is here. If I change this one to 1, it will be clear. So you can see up to 1, it's 0. From 1 to 2, it is something here, but it's 0.5, 0.05, but 2 is not included. You can see that's why this one we have a red color, but here no. It means 2 is not included, but 2 is here, right? And again, for 4, the value for 4 is here, right? This is called as a step function. Next, I want to calculate mean, variance, and standard deviation. These are key statistic measures for a random variable. For example, we have O is equal to the same 1, 2, 3, 4, 5, and 6. And we have probabilities like, for example, 0.3 for the first one, 0.25 for the second one, 0.50 for the third one, then 5%, then 10%, and then 15%. This is the probabilities of for each outcome. Then we can go for the expected value, right? Simply, we can calculate EX, right? E of X. So we can say E is equal to sum of X multiply P, right? Multiply with 4x and p in zip O and p. So what happened here? We say that we want to get multiplication of these two, right? X and p. We made a zip. Zip is a data structure using two lists. So we can say in Z, O, and P, then we want to go for multiplication of X and P, right? Then we can calculate the expected, right? So in here, I can say, in here, I want to calculate EX squared, right? So what I do here, for the same thing, but this time I say ax squared, right? So I can say e squared is equal to x squared for x squared multiply p for x and p in zip o and p. Then I can calculate variance. Variance where x is equal to e x square minus e x square, right? In this way. So we calculate v is equal to es minus e power of 2, right? And also es. And also, what is standard deviation? Standard deviation is simply a square root of the variance. So math, we can go for math sqrt of v. We didn't import math. We can import math here. So standard deviation is square root of v. Then we can print them, right? So we can say print if an expected value or mean is e, and we want to get like in 2 decimal points, right? 2 decimal points. So 2.85 is the expected value or mean. We can also print the variance, print variance v, and it is 3.23 as the variance. Also, we can print a standard deviation, print if standard deviation std, so 1.8 is the standard deviation. So this was a simple lecture about discrete random variables. Please practice and feel free to ask me if you have any questions. Thank you and see you in the next lecture.